All right, hello everyone. Welcome to my channel. This is for educational purposes and mostly the obscure and esoteric. People, in particular, people who spent their whole life working on something and came out with their, you know, magnum opus book, and nobody's ever read it. And nobody knows what it says. Um, but just because of the position that I was in my life, I read a lot of books like this and um, have quite a few favorites that I'm trying to get to a wider audience. So today is the 138th video that I've done that I'm doing on the reciprocal system of theory, which is a theory of everything that was uh, derived by Dewey B. Larson. He died back in 1990. He started his quest back in about 1930 and wrote all of his most important books, in my opinion, toward the end of his life. We're going over chapter, right now we're in chapter 2 of his um, book called Nothing But Motion. Came out in 1979, and it's the first of 3 volumes of his Structure of the Physical Universe series, second edition. And so this is really his book on physics and a little bit of organic chemistry. And his second book, called Basic Properties of Matter, is primarily on chemistry. And then his third book in that series is called Universe of Motion, which is on astronomy. He also has books on economics and other aspects of science, but especially his last book, Beyond Space and Time, which I did 100 some videos, or almost 100 some videos on earlier. Beyond Space and Time is on metaphysics, religion, philosophy, and psychology in particular. And they all come from the same theory. So he uses the reciprocal system of theory to generate answers in every subject matter. Not every, but everyone that he applied it to. And he gives you the steps and gives you the tools so that you can apply it to whatever field that you want to apply it to. You know, if you are so inclined, you could write the reciprocal system, the reciprocal theory of underwater basket weaving, or the reciprocal system of health and fitness, or, um, you know, use your imagination. Whatever your passion is, you can take the reciprocal system and figure out how to apply it to any subject. It takes a lot of work, though. Um, and so I'm trying to kind of streamline the approach for you. It's never going to be easy, but it could be as easy as your high school chemistry class. You know, a year of, a few hours a week, putting in the time, and you will eventually get it. Okay, now the basic gist of Larson's theory is that we live in a universe of motion. The universe is not made out of matter. The universe is not made out of energy. It is a universe of motion. Matter and energy are really merely specific kinds of motion, along with just about everything else, such as electric charge, electric current, magnetic flux, pressure, uh, uh, momentum, acceleration, mass, impulse. These are all kinds of motion, and they all, in Larson's system, motion is the relationship between space and time. And so every one of these different uh, specific manifestations of motion is a relationship between space and time. Matter, for example, is time to the third power over space to the third power. Energy is time over space. Speed is space over time. As we know, the car is moving 30 miles per hour, space over time. Acceleration is space over time to the second power. Force is time over space to the second power. And so on and so forth. And then that serves as a pretty iron-locked check. You can look at all of the classical theories that are out there. Check their units in terms of space and time. Get rid of the matter. Matter is time to the third power over space to the third power. So you get rid of the MKS system and you just go with the TS system or ST system. Okay, now we're in chapter 2 of this book, Nothing But Motion. He's just getting into kind of the basics of the theory. Yesterday's video, I think, was pretty crucial in terms of laying out the foundations of the reciprocal system. So you want to, you should. This is about the 9th video that I've done on this particular book. But the video from yesterday is crucial. And so we're going to start reading from Larson right here. He's just talking about how space and time have always been defined as really the container of the universe, that they are, space is something where we move in and through space. Space is like the setting that we do our actions in, and then time gets thrown in for good measure as we are moving through space-time. But in Larson's system, that is not how it happens. In Larson's system, space and time are not the container of the universe. Rather, they are the contents of the universe. The universe is made out of space and time. So that is a fundamental difference. And that's where I think we're going here once we get started. Okay, here's Larson. On this basis, space is not the Euclidean container for physical phenomenon that is most commonly visualized by the layman. Neither is it the modified version of this concept, which makes it subject to distortion by various forces and highly dependent on the location and movement of the observer, as seen by the modern physicists. In fact, it is not even a physical entity in its own right at all. It is simply and solely an aspect of motion. Time is not an order of succession or a dimension of quasi-space. Neither is it a physical entity in its own right. It, too, is simply and solely an aspect of motion, similar in all respects to space, except that it is the reciprocal aspect. Okay, given that motion is the relationship between space and time, that leaves a reciprocal relationship between space and time. When you're talking about a relation, you're talking about a fraction. So 3/2 and 2/3 are reciprocals of each other. Motion works the same way. Time and space works the same way. Time and space are the same, except that they are inverses of one another. Now, Larson here, where he's talking about how the Euclidean container for physical phenomena that is commonly visualized by the layman, Euclidean geometry is, X, Y, Z coordinates. And this should have told Larson, or maybe it actually did tell Larson, but he didn't come out with it, that Euclidean geometry is not the fundamental basis of our, geometry of the universe. Larson, after 25 years of an inductive period of study, came out with his 2 fundamental postulates. The first is basically that the universe is made out of motion. Motion is a relationship of space and time. Space and time are reciprocals of each other, and they have discrete units, and they are in three dimensions, or three or more dimensions. Um, his second postulate, though, is that the universe is follows basic commutative mathematics, and its geometry, its magnitudes are absolute, and its geometry is Euclidean. Many of his followers have strongly questioned that Euclidean aspect of the universe, and I think that has been resolved in the best way by Dr. Bruce Perret, the late Dr. Bruce Perret, who used other geometers' ideas that there is a geometrical cascade, and that the universe the universe is really projective geometry, of which Euclidean geometry is a subset. So we'll get into that more when we start looking at some of the works of Bruce Perret and KVK Nehru. But for now, we're looking at the foundation and the fundaments, and the history of where Larson is coming from. And then once we figure out where Larson's coming from, we can kind of look at some of the later people and how the theory is evolving and where it's going. And when I say how the theory is evolving, we're talking about less than 100 people here. Like, it's not like there's an entire army of people working on this stuff. Very, very few. I've actually never met a person in real life who's ever heard of Dewey Larson. And I've been studying this for over 20 years. So, it's not out there. Okay, back to Larson. The simplest way of defining the status of space and time in a universe of motion is to say that space is the numerator in the expression s over t, which is the speed or velocity, the measure of motion, and time is the denominator. If there is no fraction, there is no numerator or denominator. If there is no motion, there is no space or time. Space does not exist alone, nor does time exist alone. Neither exists at all, except in association with the other as motion. We can, of course, focus our attention on the space aspect and deal with it as if the time aspect, the denominator of the fraction, remains constant. Or we can deal with time as if space remains constant. This is the familiar process known as abstraction, one of the tools of scientific inquiry. But any results obtained in this matter are valid only where the time or space aspect does, in fact, remain constant, or where the proper adjustment is made for whatever changes in this factor do take place. The reason for the failure of previous efforts to construct a workable theory on the basis of the motion concept is now evident. Previous investigators have not realized that the setting concept is a creature of the matter concept, that it exists only because that basic concept envisions material things existing in a space-time setting. In attempting to construct a theoretical system on the basis of the concept of a universe of motion while still retaining the setting concept of space and time, these theorists have tried to combine two incompatible elements, and failure was inevitable. When the true situation is recognized, it becomes clear that what is needed is to discard the setting concept of space and time along with the general concept of a universe of matter in which it is intimately related, and to use the concept of space and time that is in harmony with the idea of a universe of motion. In the discussion that follows, we will postulate that the physical universe is composed entirely of discrete units of motion, and we will make certain assumptions as to the characteristics of that motion. We will then proceed to show that the mere existence of motions with properties as postulated, without the aid of any supplementary or auxiliary assumptions, and without bringing in anything from experience, necessarily leads to a vast number and variety of consequences, which in total constitute a complete theoretical universe. Construction of a fully integrated theory of this nature, one which derives the existence and the properties of the various physical entities from a single set of premises, has long been recognized as the ultimate goal of theoretical science. The question now being raised is whether that goal is actually attainable. Some scientists are still optimistic. Quoting Wigner, "Of course, we all try to discover the universal law, and some of us believe that it will be discovered one day." But there is also an influential school of thought which contends that a valid, generally applicable physical theory is impossible, and that the best we can hope for is a model or series of models that will represent physical reality approximately and incompletely. Sir James Jean, or is it Jeans? I'm not sure. Sir James Jean expresses this point of view in the following words: "The most we can aspire to is a model or picture which shall explain and account for some of the observed properties of matter. Where this fails, we must supplement it with some other model or picture, which will in its turn fail with other properties of matter," and so on. When we inquire, end quote, back to Larson, when we inquire into the reasons for this surprisingly pessimistic view of the potentialities of the theoretical approach to nature, in which so many present-day theorists concur, we find that it has not resulted from any new discoveries concerning the limitations of human knowledge, or any greater philosophical insight into the nature of physical reality. It is purely a reaction to long years of frustration. The theorists have been unable to find the kind of an accurate theory of general applicability for which they have been searching, and so they have finally convinced themselves that their search was meaningless, that there is no such theory, but they simply gave up too soon. Our findings now show that when the basic errors of prevailing thought are corrected, the road to a complete and comprehensive theory is wide open. It is essential to understand that this new theoretical development deals entirely with the theoretical entities and phenomena, the consequences of the basic postulates, not with the aspects of the physical universe revealed by observation. When we make certain deductions with respect to the constituents of the universe on the basis of theoretical assumptions as to the fundamental nature of that universe, the entities and phenomena thus deduced are wholly theoretical. They are the constituents of a purely theoretical universe. Later in the presentation, we will show that the theoretical universe thus derived from the postulates corresponds item by item with the observed physical universe, justifying the assertion that each theoretical feature is a true and accurate representation of the corresponding feature of the actual universe in which we live. In view of this one-to-one correspondence, the names that we will attach to the theoretical features will be those that apply to the corresponding physical features, but the development of theory will be concerned exclusively with the theoretical entities and phenomena. For example, the matter that enters into the theoretical development is not physical matter, it is theoretical matter. Of course, the exact correspondence between the theoretical and observed universes that will be demonstrated in the course of this development means that the theoretical matter is a correct representation of the actual physical matter. But it is important to realize that what we are dealing with in the development of theory is the theoretical entity, not the physical entity. The significance of this point is that physical matter, radiation, and other physical items cannot be defined with precision and certainty, as there can be no assurance that our observations give us the complete picture. The matter that enters into Newton's law of gravitation, for example, is not a theoretically defined entity. It is the matter that is actually encountered in the physical world, an entity whose real nature is still a subject of considerable controversy. But we do know exactly what we are dealing with when we talk about theoretical matter. Here, there is no uncertainty whatever. Theoretical matter is just what the postulates require it to be, no more, no less. The same is true of all the other items that enter into the theoretical development. Although physical observations have not yet given us a definitive answer to the question as to the structure of the basic unit of physical matter, the physical atom, indeed, there is an almost continuous revision of the prevailing ideas on the subject as new facts are revealed by experiment. We know exactly what the structure of the theoretical atom is because both the existence and the properties of that atom are consequences that we derive by logical processes from the basic postulates. Inasmuch as the theoretical premises are explicitly defined and their consequences are developed by sound logical and mathematical processes, the conclusions that are reached with respect to matter, its structure and properties, and all other features of the theoretical universe are unequivocal. Of course, there is always a possibility that some error may have been made in the chain of deductions, particularly if the chain in question is a very long one. But aside from this possibility, which is at a minimum in the early stages of the development, there is no doubt as to the true nature and characteristics of any entity or phenomena that emerges from that development. Okay, we're going to leave it there. Stop off and start again tomorrow with continuation of chapter 2 here. Thanks for tuning in. Have a great day, and we'll see you tomorrow.